Everyone, welcome back. We are now on to solving and graphing linear inequalities. Once again, we have an opener. I'm going to actually give you a little bit of a hint to kind of get started here. I don't know that it's all that clear, but really the first thing that you need to do, and it says here, is to create an equation in slope-intercept form of the line represented. And then you're going to replace the equal sign with the less than symbol. Now, to get you started, when we're trying to write the equation of this line, the kind of trick here is that we don't have any clear points, right? So because if you look closely, the scale is 2, right? So that first line there is 2. So we've got to kind of find those points that allow us to find the slope. Now I can pretty much safely say that's at 5, right? It's right in the middle of 4 and 6. So we're going to call that 0, 5. And then same thing down here, I found another point where x is for sure -4. And again, it looks like we can safely say that y should be -3. So we use those 2 points. Go ahead and find your slope first, which can help you write the equation of the line. And then you can go ahead and move on and answer the full opener. All right, so go ahead and pause, work through this. I'll meet you back here in just a moment. Right, here's what you should have. So my work for finding the slope over here, I use slope formula. Always a bunch of different ways you can do that. And then we have the y-intercept. I kind of gave that to you right from the start of 5. So our equation is y equals 2x plus 5. But like the problem said, we need to swap out that equal sign for the less than sign. Now, really what we're trying to do is decide, does 2, 9 satisfy the inequality? Meaning, is it a solution to this given inequality? So how we're going to do that is 2 comma 9 is really just a point, right? It's just an x and a y. So I can take 2, sub it in for the x, y, sub it in for the 9, and check this inequality statement. So 2 times 2 is 4, and after we add, we get 9 on both sides. So when I read this, it says 9 is less than 9, which is actually false, right? Even though they're equal, and that's what we're used to dealing with, inequalities is a whole nother set of rules. 9 is not less than 9, so this is false, meaning 2 comma 9 is not a solution to the given inequality. Now, we know that this was less than because of the dashed line. Had this been a solid line and we get 9 is less than or equal to 9, then this is a whole nother conversation, right? Because is 9 less than or equal to 9? Well, yes, right? It's equal to, and thus it would be a point that satisfies the inequality and is part of our solution set. So that's really what we're trying to decide with inequalities. What points make this inequality true, and how can we represent those? All right, so the first thing we're going to do is we're going to dive in and do some graphs of inequalities. So let's go ahead and jump down to this whole class practice. And let's go through these. So for the most part, the first thing we're going to do when we're graphing inequalities is we're going to graph them the exact same way we normally would. So first thing is let's graph line like normal. And one thing I want to do before we go ahead and do that, let's remember what the biggest difference is with inequalities, and that's that we have a dashed or a solid line. So we're going to graph the line like normal, but we need to decide, do we want a solid line? So solid whenever we have the or equal to, so less than or equal to, greater than or equal to, or dashed, which would be if we just have less than or just have greater than. All right, so I'm going to graph this line, y-intercept at 1, slope of -4. Tell me to go down 1, 2, 3, 1, 2, 3, 4, and write 1. 1, 2, 3, 4, and write 1. I'm going to make this graph span, or the line span the whole graph. And before I connect them, just remind myself, do I want it to be solid or dashed? Because it's less than, we want this to be dashed. And the next thing we want to do is decide, where do we want to shape? Now, a lot of you have a different set of rules, but one thing that we really emphasize in Algebra 1 is we want to be confident that we're shading the right region. And so for that to happen, we need to test a point. That's what makes sure we don't make any algebra mistakes, that we are in fact shading the correct region. So to do that, we're going to test the point. Usually that point can be 0, 0, as long as it is not on your line. If 0, 0 is on your line, you're going to need to pick something different. So when we test the point, if true, meaning once we plug in 0, 0, we get a true statement, then we want to shade towards the test point. And if false, we want to shade away from the test point. So what does that look like? We're going to take 0, 0. I'm going to sub 0 in for x, 0 in for y. And again, we can do this because 0, 0 is not on the line. And we have 0 is less than -4 times 0 plus 1. Well, -4 times 0 is just 1, or excuse me, 0. So we have 0 is less than 1, which is true, right? 0 is definitely less than 1. Since it's true, I can shade towards 0, 0, right, which is actually below the line. Now, I draw these arrows. It's especially helpful for once we start graphing more than one inequality. You don't need to draw the arrows necessarily, but it's just a habit. And that's what our graph should look like, right? So now, as soon as we throw in another equation and make this a system, the steps are essentially the same, but the one big difference is we only want to shade the one region that makes both these inequalities true. So here's what we're going to do. We're going to graph one inequality. It doesn't matter which one that is. You can start with either one, or you could graph them both at once and decide on the shading later. I like to graph one, figure out where to shade, and that way we can eliminate like half the graph right away, and then do the same thing for the second line. So let's go and graph one inequality, and if you look closely, this is the same one we just graphed, so I don't need to do any work there. I can just copy what we have up top there. So dot at 1 and down 1, 2, 3, 4. Up 1, 2, 3, 4. We know this is a dashed line. And then earlier we shaded below. Now I don't want you to shade yet. This is why we're going to use those arrows to represent where we should shade. So once we graph the other line, we should not be shading over here on this right side or above the line. We've eliminated all possibilities. Okay, our shading is going to happen down here. Now, let's go ahead and think about the second line. So let's graph the second inequality. Okay, doing the same thing as what we did above. So I have an intercept at -2, a slope of +2. Tell me to go up 2, right 1. Do it a few times. And once again, let's make sure we're either doing a dotted or solid line, dashed or solid. This one should be solid because of the or equal to. And we want to figure out where do we want to shade in terms of this line. So we're going to plug in 0, 0 to this inequality and figure out where we want to shade. So if I use 0, 0, I have 0 is greater than or equal to 2 times 0 minus 2, which is 0 is greater than or equal to -2, which is true. Tell me to shade towards 0, 0, which for this line, right, is above it. So you can see I'm drawing a bunch of arrows, okay, along this line, because it is all the points above it make that inequality true. Now, the biggest difference with systems of inequalities, we want to shade just the one region that makes both inequalities true. So shade the region that makes both inequalities true. Now, the reason we drew our arrows is it helps us find where both inequalities are true. So we said right from the get-go, after I graphed that first line, that we can't graph this right side at all. And so as I eliminate that, which you can use with your hand or follow the arrows, right, we're looking at either this top left or this bottom right. Well, we decided we also have to be above this line. So this region does not work. So it has to be this top left region. And the arrows really help us keep track of which region are allowing the inequalities to be true, or what points are making that inequality to be true. And that's it, all right? So if you go ahead and flip this thing over, I'm going to have you all hit pause and then go ahead and graph number 3 and 4 on your own, and we'll come back together and discuss them. Right, welcome back. Here's what you should have. Number 3, pretty straightforward, nothing weird that happens. After you test 0, 0, you get that it's false. And so we want to shade away from 0, 0, which is actually above the line. Right, so 0, 0 didn't work, so shading away is just the opposite side, and it should be above that line. Now, when we get to number 4, there's a couple things that are a little off. The first thing I noticed is I have x and y on the same side in that top equation. So I could come up and graph the x and y intercepts like we learned in our last lesson, or we can get y by itself. Now I'm going to get y by itself by subtracting 2x, and now it's in the form of mx plus b, makes it a little bit easier. All right, so we have an intercept of -1, a slope of -2, and then I figure out from there that it's less than, and so I plug in 0, 0, and I get 0 is less than -1, which is false. So I'm shading away from 0, 0. Which is below that line. Now the next equation, be careful, it is sneaky. I see 2y plus y. Well, those are like terms. We need to combine those together, and that gives us 3y. Now, I don't know about you, but I've never graphed an equation with 3y. So I'm like, I can get rid of that 3 by just dividing both sides by 3. So when I do that, we get y is greater than 1. Now, thinking about what that looks like on the graph, remember, we're really graphing the line y equals 1, meaning we want to graph a line that every coordinate has a y coordinate of 1. And that would be a horizontal line at 1. And that's what you're seeing here. This is y is greater than 1. Now again, when we decide where we want to shade, we're going to plug in 0, 0, and I get 0 is bigger than 1, or 0 is greater than 1, which is false, right? 0 is not greater than 1. So 0, 0 is below the line. I want to shade away because it was false. So as we figure out what region makes both true, right, we can cover up the half that we know for sure doesn't work, and it ends up being this top left section. All right, so that's part of inequalities. The next set is going to be solving them. And the one difference that we're going to start doing in Algebra 2 is we're going to write our solutions in interval notation. So go ahead and slide your paper down, and let's take a look at the way we're going to write our solution set to inequalities. All right, so I'm going to have you all try this on your own. Maybe I'll just show you one real quick just to get a quick reminder. But if I give you the number line, I want you to write what that number line is showing in interval notation. Right, so it's at -5. That is a filled in circle, meaning we want to include it. So anytime we include the value, we use a squared bracket, and that is our lowest. And then we go comma, and then we want to write our highest value next. So how far is this line going? It's going all the way to positive infinity. There's no sign of it stopping. Whenever we go to positive infinity, we need a curved bracket because we never actually get to infinity, right? If you tell me the highest number you can think of, I can get one, at least one bigger every single time. So infinity always has that curved bracket, right? So then for this one, you're going to draw the number line that is represented by this interval notation, and then just the opposite here, write it, the number set in interval notation, and draw the number line. So go ahead and hit pause. Go ahead and do that real quick. All right, welcome back. Here's what you should have. Let's talk about the second one here. And what this is showing, this reads -infinity to 4. We're going to include 4. And this is that union symbol, meaning we're going to include the numbers from 6 to infinity. So I just break it into pieces. How do I represent that? Well, this is going to be -infinity, so all the numbers to the left of 4. And that's what this left part is showing. And then we're going to get all the way to 4. We're going to use a closed circle because of the or equal to. And then we're going to pick back up at 6 with an open circle because of the curved bracket and go all the way to positive infinity. So this is a compound inequality, something we're going to talk about on the next page here. The next number line, this is another compound inequality. And so we're just representing the numbers in between -8 and -1, both using curved brackets because of the open circles. And so it's just from -8 to -1, lowest number to highest number. And last one, pretty straightforward. We're going to include -2 with a closed circle and just shade to the right, meaning we're shading all the numbers that are greater than -2. All right, go ahead and flip this thing over. Let's talk about how we're going to solve inequalities, more specifically compound inequalities. All right, so with compound inequalities, I know we really haven't talked about solving inequalities in this lesson, but it really is just the same as how we would solve an equation. There's one difference, that's that testing the value, and I'm going to show you how we're going to do that here in just a second. All right, so when solving in inequalities, one thing that needs to happen is we want to shade the numbers that make both inequalities true. And that's what we need here. So we need both inequalities to be true, and that's where we're going to shade. So to solve these, we're going to split up the equations. Let's go ahead and do that right now. So when I say split it up, right, we're used to having, or at least we're not used to seeing an inequality symbol and another inequality symbol with the equation right in the middle. So we want to make this in something that we're familiar with. So if I hide or take away one of those inequality symbols, what's on the right, I have an inequality statement right here, and I'm going to write that down. So I have 36 is less than or equal to 11 minus 5x. Now we're going to do the exact same thing on the other side, but I'm going to hide the other number, or the left side, and that inequality symbol. Like 11 minus 5x is less than 66. So now we have split the two equations into ones that we can solve. It's still and, meaning we want both to be true. So now we're going to solve them like we normally would equations. So solve just like you would an equation. Meaning we're going to change, we are used to solving equations, not inequalities, so I'm going to make it an equation. I'm going to rewrite this. 36 equals 11 minus 5x, and then 11 minus 5x equals 66, which we can solve each separately. So subtract 11 to get 25 minus 5x. I get that x equals negative 5. Minus 11 over here as well. I get 55, and the x equals negative 11. So we call these two numbers our anchor points. Now, as soon as we're done with that, we're going to go ahead and make our number line. Negative 11. We've got negative 5. I'm going to put a number in the middle. You'll see why in just a second. Let's use negative 7. And then we need to decide, do we want to use a closed circle or an open circle on these? This can be kind of tricky depending on the setup of the inequality. So I'm following this up. I'm like, okay, the anchor point of negative 11, which is over here, came from this inequality symbol, which is less than. So that needs to be open. Then the other anchor point of negative 5, follow that up. I say it's less than or equal to. So that one needs to be closed. Now we want to decide, where do we want to shade? Most of the time, and this is like 99% of the time, inequalities will shade in between, but we're going to make sure of that, right? So when deciding where to shade, we're going to test a point, which we've done a lot of, right? We did this just on the other page. Now, when possible, we want to test 0. Okay, it's really just 0, not 0, 0 on a number line. But what helps is if we just test a number in between our two anchor points, we can decide if it works, we're going to connect our two anchor points. If it doesn't work, when we plug in that number in the middle, then we would shade away. And this really helps to make sure we're keeping track of everything correctly and thus coming up with the same number line. So let's test negative 7. I'm going to do that up here. So test negative 7. I'm going to plug negative 7 into the inequality, and we're going to check, do we get something that's true or false? So 36 is less than or equal to 11 minus 5 times negative 7, which is less than 66. So 36 is less than or equal to 11. That's going to be plus 35, which is less than 66. So 36 is less than or equal to 46, which is at less than 66. So we're left with this weird statement here, and we can just check it. So is 36 less than or equal to 46? Yes, it is. Is 46 less than 66? Yes, it is. So what that tells us is that negative 7 made this inequality set true. So we're going to connect them. After we connect them, the only thing left to do is just like we did on the last page, and that's to go ahead and write the inequality statement in interval notation. So this represents that we're going from negative 11 all the way to negative 5 with a curved bracket. So the number line and the inequality statement all represent the solution. So we need both, right? So we're going to split equations, solve just like you would an equation, create number line, and then decide where to shade by testing a number. Now, in this example, I tested a number that was in the middle of the two anchor points. Doesn't necessarily need to be that, but I know, again, if it's true, I'm going to connect them. If it's false, I would shade away. All right, so now when we get to or, it says we need just one of the equations to be true. So we need either, doesn't matter which one, to be true, and that's what we're going to shade. So the difference between these two, think about if your parents said, I need you to vacuum and take out the trash. They're expecting you to do both of them, right? They need you to vacuum and also take out the trash. But they said, hey, will you take out the trash or vacuum? You just need to do one of those two. I'd probably take out the trash, a little bit easier. I guess it depends on how much trash you have, right? But that's important that we can distinguish between these two examples, right? So to solve these, it's really what we did here, but we don't need to split it up. The splitting up has already happened. So we're going to solve like normal. And then create number line. And decide where to shade. All right, so let's just go ahead and solve this left one first. I'm going to make it an equal sign. Add 3. I get the x equals 7 as one of my anchor points. Over on our other equation, I'm going to add 10. The x equals 9. All right, so now we're going to go ahead and create our number line. So I have 6, 7, 8, and 9. Again, let's figure out if we want dashed or excuse me, open or closed circles. I'd look at both of them, and they're both open because they're both either less than or greater than. So open circle at 7, open circle at 9, and we want to decide, do we want to shade to connect or shade away? It's always going to be one or the other. With or, almost always, you will shade away from the 2 anchor points. And we're going to do this by testing 8, just like we did up top here, or test a number in the middle. I'm going to test it for both, though, okay, because this tells me exactly where I'm going to end up shading. So if I test 8, I get 2 times 8 minus 3 is less than 11. So 16 minus 3 less than 11 is 13 less than 11. That is false. So what is that telling me? That tells me for the anchor point at 7, since it's false, I need to shade away from the number I tested. Since we tested 8, away from that is to the left. Now already this is kind of telling me most likely I'm going to shade to the right of 9. But again, let's confirm it by testing 8 or a number in the middle. So negative 8 times 8 minus 10 is less than negative 82. Negative 64 minus 10 less than negative 82. So negative 74, is that less than negative 82? No, that's false, right? So once again, since it's false, we want to shade away from the number we tested. 8 is in the middle, and it does not work, so I need to shade away, which is to the right. And now we have our number line. The only thing left to do is to write what this number line is showing in interval notation. So I'm going to say we have all the numbers to the left, which is negative infinity, all the way to our first anchor point of 7. It is curved because we're not including that number because it's open. Then union, meaning including the other set of numbers from 9 all the way to positive infinity. And there is our full solution set. All right, now I'm going to go ahead and allow you guys to get some practice on your own. So go ahead and hit pause. I will show you what you should have in just a second, and then we will wrap up this video right after that. All right, welcome back. Let's go ahead and talk about these, and we're going to actually come back to number 5 as something weird happens there. Hopefully you all picked up on that. I'll get to that in just a second. But let's look at number 6. Pretty straightforward, exactly like the example. I split up the 2 equations, first changing it to an equal sign right away. And when you solve it, it becomes pretty quick that we get an anchor point at 2 and an anchor point at 9. So after I plot those, again, I find a number in the middle, which just happened to be 5. You could choose any number in the middle to test this and just confirm that we are going to shade together, because we don't want to assume anything. That's the problem with her first example. But let's go ahead and just test this. So when I plug in 5, and we're plugging it into the original inequality. So the left side here is really what I'm plugging it into. Okay, so each x is switched out for 5, and I get negative 25 minus 7, which is negative 32. Is it less than or equal to, after we simplify the right side, negative 29? And that's true, right? Negative 32 is less than negative 29, telling me to shade to the right. So as I shade to the right, right, that looks like we're going to connect it, but we're going to make sure that it is also true for the other side of the inequality. So I get the anchor point of 9, and we're going to test 5. So when I plug in 5, just like before, this time it's that right side with the inequality. We end up getting that negative 29 is less than negative 21, which is also true, telling me to shade towards 5. So when I shade towards 5, we end up seeing that they do get connected. So the shading, or at least the testing, I'd split them up differently, which is fine. I could have plugged in 5 to the original here, like I had shown you above. Either way, you should have seen that you get something true, meaning the middle works, and we can connect them. This shows that we are shading numbers from 2 all the way to 9. Make sure we're writing an interval notation. All right, let's come back to this first one. And everything seems to be just fine. You solve the left side, you can anchor point at negative 2. When you test 0, we can test 0 because it is in the middle this time. I get that as false, and it's telling me to shade away, which is what I would think because it's an OR inequality. Now, for the right side here, I start to see that as I solve it, we get an anchor point at 5, and I test 0, and we get 10 times 0 minus 10 is less than 5 plus 7 times 0. Well, once we simplify that, I get negative 10 is less than 5, which is true. So I'm like, okay, when it's true, I want to shade towards a number that we tested, which is towards 0. So I'm shading to the left. I'm like, that's odd, right? If I'm shading to the left, this isn't an OR inequality, or at least not what we're seeing on the number line. OR inequalities are supposed to shade away from one another. This is why we test values. This is why we're able to catch some of those mistakes. So even though most of the time OR inequalities will shade away, not 100% going to be the case. So we just adjust, right? So what is this showing? This is actually a good number line. Well, this is showing we have numbers all the way from negative infinity. And then we get to this number here, that first anchor point of negative 2. But the problem is we don't include negative 2. We'll include everything up to negative 2, so negative 3.00000 or negative, what would that be? 2.00001, okay, and beyond. But we're not include exactly negative 2. So this is a curved bracket. And then we got to pick it up on the other side of negative 2, which would be negative 1.9999999. So negative 2 really. And that goes all the way to 5, where we do not include it. So the inequality or the interval notation does look a little bit different here. And again, this is a perfect example as to why we test and to why we use the methods that we do to come up with these inequality statements. All right, the rest of this, that's it for this video. Now is your turn to practice.